Imagine your ARM7 processor is running a program and suddenly a timer interrupt arrives, a memory error happens, or an unknown instruction is detected. Does the processor continue running the same code? No. It immediately switches into a special operational state designed to handle that situation. These different operational states are called ARM7 processor modes. What is an ARM7 processor mode? In ARM7, a processor mode defines the current operational state of the CPU. It tells the processor what type of task it is handling, what level of access it has, which set of registers it should use. ARM7 has 7 modes. These modes are divided into two categories: non-privileged and privileged. The only non-privileged mode is user mode. This is where normal application programs run. In user mode, access to hardware is restricted. Critical control settings cannot be modified directly. It cannot directly enter privileged modes. All other modes are privileged modes. These modes have higher access rights. They are used for operating systems, exception handling, low-level firmware. If you compare non-privileged and privileged modes, non-privileged mode cannot directly change important CPSR control bits, disable or enable interrupts, switch itself into privileged modes, access certain system level operations. But if you consider the privileged modes, they have higher control over the processor. They can modify CPSR control bits, enable or disable interrupts, access hardware directly, change processor modes. User mode acts as a regular employee which can do normal tasks, cannot change company settings. But privileged mode acts as an administrator which can easily modify system configuration. Now let us understand each ARM processor mode in detail. First of all, we have the user mode. User mode is the normal program execution mode. When you run an application, ARM7 normally executes here. It uses the normal register set. No extra banked registers are available in this mode. One thing you should note here is user mode can read CPSR and can update conditional flags, that is N, Z, C and V flag, only through normal instructions, but cannot directly modify CPSR control bits such as T bit, interrupt bits or mode bits. While any of those privileged modes can read and write both CPSR conditional flags and control bits, allowing them to change execution state, interrupt settings, and processor modes. Next, we have system mode. System mode is a privileged version of user mode. It runs normal code but with full access privileges. It shares the same registers as user mode. Operating system tasks can use this mode. Supervisor mode. Supervisor mode is entered after reset or when a software interrupt occurs. For example, when a program requests an operating system service using the SWI instruction. In this mode, ARM7 gets special banked registers. They are R13, R14 and SPSR, which is nothing but stack pointer, link register and saved program status register. IRQ mode. IRQ means interrupt request. When a normal hardware interrupt occurs, ARM7 enters IRQ mode. For example, timer interrupt and external device interrupt. IRQ has its own banked registers. They are R13 IRQ, R14 IRQ and SPSR IRQ. This allows faster interrupt handling. FIQ means fast interrupt request. This is the fastest interrupt mode in ARM7. And why exactly is it faster? Because FIQ has more banked registers. It gets R8 to R14 FIQ and SPSR FIQ. Since FIQ already has its own registers, the processor spends less time saving and restoring data. FIQ also has higher priority than IRQ. Abort mode handles memory access problems. For example, when a program tries to access invalid memory. There are two types. One is prefetch abort, that is problem when fetching an instruction, and then we have data abort, which is problem while accessing data. And abort mode has these banked registers, that is R13, R14 and SPSR. Undefined mode. This mode occurs when ARM7 detects an instruction that it does not understand. For example, executing an unsupported instruction, it uses R13, R14 and SPSR banked registers. Now the question is, how does ARM7 know which mode it is currently in? The answer is CPSR, that is the current program status register. The lower 5 bits of CPSR are called mode bits. They indicate the current processor mode. These are the binary values of CPSR mode bits associated with ARM7 processor modes. When an exception occurs, ARM7 hardware updates these bits automatically and switches to the required mode. Why banked registers? ARM7 programmers see registers, that is R0 to R15, but internally ARM7 has multiple copies of registers depending on the mode. These are called banked registers. The ARM7 architecture usually contains 37 registers internally. Banked registers allow the processor to switch modes quickly without saving everything to the memory. Now, one important practical point about ARM7 modes. In systems with an operating system, normal applications run in user mode with limited access. The operating system uses the privileged modes to handle hardware, interrupts, and system level operations. But in case of bare metal programs like Keil, ARM7 assembly projects, there is no OS. So the program usually starts in supervisor mode. Our code usually continue executing in supervisor mode unless we explicitly switch modes. Supervisor mode is used during the startup because the processor needs full control to initialize the system. Understanding processor modes is a foundation for understanding interrupts and embedded systems on ARM7.